Hi everyone. For this video, I'm going to show you some of examples from Fourier Transform applications, which is chapter 3. Okay, so we begin with this question. This is from the past year final exam 2020-2021 semester 1. Okay, so I'm going to read this question. A multiplexer, the multiplexer configuration of a transceiver system is illustrated in figure Q4C. This is the figure Q4C. The system is designed to transfer two modulated input signals, X1MT and X2MT, from the transmitter TX via a single channel as a multiplex signal MT. At the receiver, Rx, MT is demultiplexed by using the unity gain low pass filter, which is called as LPF, and high pass filter, HPF, for further processes. The frequency spectrums such as provided in figure Q4C1 are obtained from the system. So this is a figure Q4C1. To summarize this question, basically we have transceiver system. We have this part, which is the multiplexer, and this is the demultiplexer part. So at the multiplexer, the inputs are two signals, X1 and also X2T. So both of these signals are modulated using carrier frequency cosine omega CT. Okay, so this is the modulation process, and the output from the modulation process, which we called as modulated signal, X1MT and also X2MT. Both of these signals are summed together, okay, before it is being transmitted as MT. Okay, so both of the signals are summed together to be transmitted as MT. So this MT will be transmitted via a single channel. This is what we call a channel, this line here. Okay, and this is what we call multiplex signal. Okay, because this signal is from X1 and also X2M summed together. So at the demultiplexer, okay, which is at the receiver part, okay, so this side here is the receiver part. Okay, both of these signals, these MT signals goes through two different systems. The first one is high pass frequency, okay, and the second one is low pass frequency. Okay, basically K1 and K2 the gain for the HPF and also LPF, okay, to produce two signals, Y1T and also Y2T. So the information that are given here is, first, this is X1 omega. So X1 omega here is actually the Fourier transform of X1T. So this is the Fourier transform of X1T. And for this M omega here is the Fourier transform of MT. So MT here is the multiplex signal. X1 here is the input signal. Okay, so please be noted that this X1 omega is the Fourier transform for this one, X1T, not X1 MT here. Okay, so this is the original input signal. This is the multiplex signal. And Y1 omega here is the Fourier transform of YT. So from this information, we need to answer a few questions. Okay, so the first question here is, express the spectrum M omega of the multiplex signal MT mathematically and then determine the carrier frequency omega C. So I put again the information here. This is from the transceiver. Okay, so from the transceiver, we know that MT here is the multiplex signal, okay, which the spectrum is given as M omega here. Okay, and also we need to determine the carrier frequency. So we need to be able to understand this information, okay, which X1M here is actually the modulated signal from X1. Okay, so M here is the summation of X1M and also X2M. Okay, so first we need to express the spectrum mathematically. Okay, so don't panic. We do not have to actually put the equation of this line here. No, we don't have to do that. We just have to put what we understand mathematically. So firstly, what we need to write is empty is actually from x1 empty plus x2 empty. Okay, this is the mathematical expression for empty in terms of time domain. And x1 empty is actually x1t cosine omega ct. Okay, and x2 empty is actually x2t cosine omega ct. So both x1 and x2 are modulated using the same carrier frequency, okay, which is omega c. So we need to determine the omega c here. Alright, so from mt here, since we already write the equation in terms of time domain, we can now write the equation in terms of frequency domain. So we need to understand this m omega, the spectrum of m omega, is the Fourier transform of mt. So m omega here is the Fourier transform of mt. So how do we Fourier transform this one? Okay, so we need to be able to use the formula for Fourier transform. Okay, so you have to go to the table of Fourier transform. So from the table, we know that, okay, this is the modulation properties. So for modulation, if we have ft cosine omega naught t, okay, the Fourier transform of this function will be 1 over 2 f omega plus omega naught plus f omega minus omega naught. So in this case, f here is actually the m. Okay, so what we need, f here is actually the x1. So what we need to do here is we have to Fourier transform this part, then and also Fourier transform this part, right? Okay, so we write the m omega, the Fourier transform for the mt means the Fourier transform for the whole equation here. This first part here is 1 over 2. So we just write in terms of x1. Okay, omega naught now is actually omega c. So omega plus omega c plus x1 omega minus omega c. Okay, this is the first part, which is m omega x1 part, okay, which has been modulated. And the second part here is x2, because m is the summation of x1 and x2. So this is 1 over 2 x2 omega plus omega c plus x2 omega minus omega c. Okay, so we just leave it like that. So this is the spectrum m omega when we have expressed mathematically. Okay, once we have determined the m omega mathematically, then we can find the carrier frequency. Okay, so do not confuse with x1 mt. Okay, x1 mt is actually x1 which has been multiplied by cosine. So what we have here is this whole equation here is actually x1 m omega, and the whole equation here is actually x2 m omega. Okay, so now we want to find the carrier frequency. So we have to observe at the figures given here. We have x1 omega, okay, and we have m omega, which the highest amplitude here has been divided into 2. Okay, this is the highest amplitude here is 4, and the highest amplitude here is 2. So this explains why m omega is actually half of the amplitude of x1, right? So we know that m omega here is the modulated signal of x1. But we also notice that the shape is slightly different. So we focus on the shape which is the same here. So if you see this shape here, is actually the same as this shape here. Okay, so we focus on the highest amplitude. The highest amplitude here is 4, which occurs at omega equal to 0. The highest amplitude here is 2, okay, which occurs at negative 50 and 50. So this explains that, and the original shape of S1 here is this part. Okay, because we have to remember that m omega is the summation of S1m and also S2m. So it means that the another part here, okay, that looks like triangle here, this actually comes from a different signal, which is S2m. Okay, so from there we can conclude that the omega here is 50 because it has been shifted to the left, okay, which is plus 50, and to the right, which is negative 50 here. Okay, so basically we look at the origin of the signal. The origin of the signal here, omega is equal to 0. Okay, where the highest amplitude here is 4. So the highest amplitude here is 2. It happens at omega equal to negative 50 and also 50. So now we can see that from the figure, it can be determined that omega c is equal to 50 radian per second. So don't forget the unit here. Right? So now we answered the question number 1. Continue to question number 2. Based on figure Q4C, the modulated signal of signal X2T, okay, is given as, okay, so this question is talking about this X2MT is given as X2MT is equal to X2T multiplied by cosine omega CT. Okay, so X2M is equal to X2 multiplied by cosine omega CT, which is also equal to MT minus X1 MT. Okay, so S1 MT is also XT cosine omega CT here. So express the spectrum of the above time domain expression mathematically, and then represent the spectrum X2M omega, okay, which is the Fourier transform of X2MT, and also X2 omega graphically. Okay, so again we need to make use of the information that we have the information that are given here. So this one is ft of X2MT, and this one is the ft Fourier transform of X2T. Okay, so now we need to express the spectrum of this time domain expression mathematically. So we just make use of the equation given here. Okay, so we need to express spectrum of the above time domain. So we need to express the X2M omega. Okay, basically we need to Fourier transform the signal X2 MT. So again we use the modulation properties in the table C1. Okay, table of Fourier transform. So from the table we know that ft, I write it here again, cos omega naught t. When we Fourier transform this signal, we will get 1 over 2 f omega plus omega naught, okay, plus f omega minus omega naught. So in this case, omega naught here is omega c, okay, and we just put in we just use this equation here. So the Fourier transform of X2T will be, because this is modulated with cosine, so 1 over 2 X2 omega omega plus omega c. And now we have determined before from question 1 omega c is equal to 50. So we just put 50 here plus X2 omega minus. Okay, so I'm gonna erase this part here. Okay, because this is just from the table. Alright. Okay, and then we already have this, and if we want to express in terms of this equation, okay, it's also accepted. for the solution, this is m omega minus 1 over 2 x1 omega plus 50 to, oh sorry, this is x1. So again, omega minus 50. Okay, so I repeat here, x2 m omega. Okay, if you want to express in terms of mathematical expression, we just have to Fourier transform the signal in time domain x2 mt. Okay, so if we use this equation, it is just 1 over 2 x2 omega plus 50 plus x2 omega minus 50. Okay, so this is the Fourier transform for x2 m omega. Alright, and then if you want to use this equation, so either one is accepted. Alright, m omega minus 1 over 2 x1 omega plus 50 plus x1 omega minus 50. So remember, 50 is the Fourier frequency which we have answered before. Omega c is equal to 50. Okay, so now we want to represent the spectrums and x2m omega and also x2 omega graphically. We want to find the spectrum x2m omega, so we have to work backwards. Okay, we have to make use of the information that we have here. Okay, we have to make use the information of x1 omega and m omega. So I redraw m omega here. We know that m omega is the multiplied signal and also modulated signal. Okay, and also we know that x2m omega is actually m omega minus this part. Okay, so this part, okay, the one that I have circled here, this part is actually x 1 m omega. Okay, so m omega minus this part is actually x1 m omega. So we need to draw the x1 m omega. So x1 m omega is actually half, okay, of the amplitude of x1, which has been modulated and shifted to 50, and also negative 50 here. So we have x1 omega. Okay, let's draw x1 omega with the new amplitude, which is the highest amplitude here is 4. So the new highest amplitude, okay, and also it has been shifted to negative 50 and also 50. So it should be like this. This is negative 50. So this one starts from 0, shifted to here, and the shape should be something like this. Okay, because we have to follow this shape. The highest amplitude here is 2. So let make the amplitude here is 2. Okay, the same as m omega. So this is 2. So we draw like this, and then this should be 1, and 1. This one. Okay, this one is at 1. So this one, when we want to change the signal, should be at half. Okay, so the drawing. So I hope you understand what I'm trying to say here. Okay, so this is the signal for x1 omega, which has been shifted to negative 50, and also this part is also shifted to 50. Okay, and this part, okay, the end of the signal at negative 50 shifted to 0. Okay, because basically you shifted to the right by 50, so this point should be at 0. Okay, for this part. Okay, for the positive part. Okay, on the other hand, this point, okay, should be at negative 75, because this is negative 25. So when we minus 50, we will get negative 75. So why we minus 50? Because omega c is 50. So we want to shift this to the left. Okay, and this point here, negative 50, we minus another 50, we will get 100. Okay, so this is for the negative part. For the positive part, we need to add all this omega here by 50. So negative 50 plus 50 is 0. So we will have 0 here, like this. Okay, and this point should be at 1 over 2. Why? Or 0.5. Why? Because this point is at 1. Okay, the amplitude here is 1, x1 omega. But for x1 m omega, the amplitude, all the amplitudes that we have here, okay, is being divided by half because of 1 over 2 here. So this is 1 over 0.5. Okay, so my drawing should be better. Okay, and then we goes up to this is 3, so basically to around 1.5. Okay, and then the highest amplitude here is 2. Okay, it goes down. Okay, so basically the point here is negative 50 plus 50 is 0, negative 25 plus 50 is 25, and 0 plus 50 is 50. So this is x1 m omega. Okay, but we have not answered the question. We have not answered the question because the spectrums that the question wants here is x2 m omega. Okay, so m omega minus x1 m omega. If we observe these two spectrums here, okay, so we should notice that the part that is missing at x1 m omega here, sorry, the part that is missing at m omega, which is not exist at x1 m omega, okay, which is the triangle here. Okay, so I repeat here, if you observe these two signals, okay, x1 omega doesn't have this triangle, but m omega has. Okay, it means that this part here should come from another signal. So another signal here is x2 mt. Okay, which when we Fourier transform it, it will become x2 m omega, right? So we will draw the result, the signal, okay, the output signal, the resulted signal, which is x2 m omega. Okay, it should have the same I mean the amplitude here should be half from x2 omega. Okay, x2 m omega should have the same shape as x2 omega, but the amplitude is half. Okay, so we just take this from m omega here, this part, and we draw it again. Alright, so this part we have, okay, sorry, my drawing should be better. Okay, so the part here that we should angle, which represents x2 m omega, so this is negative 50, 0, this is negative 25, sorry, this is 25, so this is 50, and the signal stretch until 100. Okay, so again, if we work from here, we know that m omega is the summation of x2 m omega and x1 n omega. So if we add these two signals here, okay, this part we add with this, we will get this. This part, okay, at the positive part, if we add with this, we will have this. Okay, so the one that I circled in yellow is the x2 m omega, okay, which comes from x2. Okay, original signal here is x2, and this part here, okay, the one that I circled right now, comes from x1 m omega, which originally comes from x1. Okay, so I understand what I'm trying to say here. So now we have x2 m omega. We can draw x2 omega, but we have to work backward because x2 m omega is the modulated signal, and also I forgot to put here the amplitude. The highest amplitude here is 1 because we follow what we have in m omega here, which the highest amplitude is 1. Okay, for x2 m omega. So it means that for x2 omega, we need to have the amplitude which is times 2 from this one. Okay, why? Because x2 m omega, okay, x2 m omega here is actually half from, okay, the amplitude here is half from x2 omega. Okay, x2 m omega, the amplitude here is half, okay, half because of this from x2 omega. So we should draw the same shape for x2 omega with this one, but we only have one component because it has not been modulated, and the highest amplitude should be double by this one, so it should be 2. So we will draw it again. We want to represent x2 omega. Okay, we have already represent x2m omega, okay, from the previous answer. So for x2 omega, we know that the shape is the same, but the amplitude should be 2. Okay, and we also know that x2m omega is x2 omega which has been modulated. So when we say modulated, means it has been shifted, and we know that omega c here is 50 rad per second, radian per second. So means that it has been shifted to negative 50 and also 50. So the original should be the original x2m omega should be at 0. The amplitude, the highest amplitude should be 2. Okay, and the width of the signal is 100 minus 50 is 50. So it should be at 50 here. Okay, so this is the original signal, which is a triangle signal of x2m omega. So now we have answered question 2, both of question 2, by drawing the spectrums of x2m omega and x2 omega. So please be noted that for question 2, we have 3 different questions. First, we need to express the spectrum of the above time domain expression mathematically. So basically, this normally the marks given is actually 2, and this one 2, and this one 2. So we have 6 marks for all 3 answers here. Okay, moving on to the next question. Okay, still in the same question for final year exam. Okay, so for the next question, express the spectrum y1 omega of signal y1t mathematically, and then obtain the cut-off frequency of the high pass filter and gain k1. So we have 2 different questions here. The first question is to express the spectrum y1 mathematically. The second question, we need to obtain the cut-off frequency of the high pass filter. And the third question is we have to obtain the gain k1. Okay, so we know that this is a high pass filter, so we have to write the equation of the high pass filter. Okay, first we need to understand that y1 is actually empty that goes through the high pass filter. So the operation here is actually convolution. Okay, and k1 is the gain of the high pass filter. So the way that we need to write mathematically is if y1t equal to mt convolve with k1 multiplied by h1t. Okay, this is in terms of the time domain, but we need to put in terms of spectrum y1 omega. So from here, you can just write y1 omega. Basically, we have to Fourier transform this whole equation equal to m omega multiplied by k1 h1 omega. So h1t is the impulse response, okay? And when we put in terms of Fourier transform, it becomes h1 omega, and this h1 omega is the equation of the high pass filter. So this is the equation of high pass filter. Okay, so we put m omega multiplied by k1. The equation for high pass filter should be like this. So this one is you need to understand. And also remember omega divided by 2 omega c naught. So this omega c naught is the one that you need to find. This is the cutoff frequency of the high pass filter. Okay, so we can find it based on the given information here. Okay, so based on this, so we have answered the first question here. Okay, express spectrum y1 omega mathematically. So based on this equation, okay, we can draw the high pass filter. So the high pass filter should look like should look like something like this. We need to have this cutoff frequency, negative omega c naught and also omega c naught, and the gain here is k1. So this is h1 omega, okay, which is the high pass filter. Okay, so this high pass filter is being multiplied with m omega. So this is m omega. We multiply h1 omega with m1 omega, so we will have this y1 omega. So we need to observe actually. Okay, we need to observe. Okay, m omega has the highest frequency of 2. y1 omega has the highest frequency of 4. Okay, so from here the shape is also consistent here. Okay, so what we have here is this part. Okay, what we have at y1 omega from m omega. Okay, so you have to observe. Okay, you have to observe and also imagine. We have this part. Okay, for this, right? And we also have okay, if we look here, we have the triangle part at 50 to 100. So this is also similar to this, right? But the amplitude here is 1 and the amplitude here is 2. So from the observation, we can conclude that K1 is equal to 2. Why? Again, okay, the highest amplitude here is 2, the highest amplitude here is 4. So 2 times 2 is 4, so K1 is 2. And this one, the highest amplitude for the triangle here is 1, the highest amplitude here is 2. So 1 times 2 is 2. So K1 is equal to 2. In terms of omega C naught, okay, so this one is actually equal to 2. In terms of omega C naught, we know that if you imagine that the filter here is on top of m omega, so let's imagine that. Okay, let me choose the yellow color here. Okay, so we know that only this part is retained. Okay, and also only this part is retained. Okay, so we imagine like that. Alright, okay, so if we imagine like that, okay, this yellow color means the high pass filter. So we can see that the omega involved here is 50. So from here we can also conclude that omega C naught is equal to 50 radian per second, because high pass filter, okay, has filtered spectrum between or within omega equal to negative 50 or bigger than negative 50 and less than 50. So only the one that I have circled here is retained, okay, and all other parts here in the middle here are removed. Okay, so that is why omega C naught here is 50 radian per second. So now we have answered the question 1, 2 and also okay, from the same question, this is question 4. Okay, from the same question, finally exam, express the spectrum y2 omega of signal y2 mathematically. Okay, again, so we have to express y2t in terms of Fourier transform mathematically. Then, if given cut-off frequency of the LPF and gain K2 as 50 rad per second and also 3/2, which is the gain K2 respectively, represent. Okay, so we have two questions here. First, we have to express y2t mathematically, y2 omega mathematically, and second, we have to represent the spectrum graphically. Okay, so basically we have to write equation and also we have to draw the spectrum y2 omega. So now it is given that the LPF here, okay, omega C naught is equal to 50 rad per second and K2 here is equal to 3/2. Okay, and then we write the equation of y to t first mathematically. So y to t is equal to mt. Again, this is we have mt here. Okay, this is from mt goes to low pass filter. So basically, low pass filter have gain k2, okay, and also impulse response h2t. So the process here is if we are talking in time domain, is convolution, but when we analyze in Fourier transform domain, okay, basically it becomes multiplication. So in time domain is convolution. Okay, so in Fourier transform, if we write in terms of frequency domain, we have transformed Fourier transform of this equation. We get m omega multiplied by k2 h2 omega. Okay, so this is m omega multiplied by k2, and this h2 omega is low pass filter. So we need filter is rectangle omega divided by 2 omega c naught. So omega c naught is given as 50 per second, and also k2 is given as 3/2. So we put in the equation, it will become m omega multiplied by 3/2. Okay, rectangle omega divided by 2 multiplied by 50 is 100. Then we have this one. Okay, so once we obtain the equation for the low pass filter, we can draw the low pass filter here. So what we have now here, okay, has the amplitude of 1.5, okay, and the cutoff frequency for negative 50 to positive 50. Okay, so now we have to represent spectrum y to omega. This is something that we don't know, but we have the equation. Okay, so basically you just have to imagine that this h2 omega, okay, is multiplied by m omega. So if we draw this h2 omega on top of m omega here, okay, with the cutoff frequency 50, so it will be something like this. Okay, but the gain here, okay, so you just imagine that the gain here is 3/2. Okay, so basically we retain whatever in the box here, okay, in the yellow box here. So we can draw the y2 omega, and also the highest amplitude here. If we look here, so what we have to do is we'll multiply by 3/2. 2 multiplied by 3/2 is 3. Okay, so the final spectrum for y2 omega should have the highest amplitude at 3. Okay, and also this label here to make our work easier. Okay, and also the frequency involved 5, 50, 0, 25, and 50, and negative 25, and also 50. Okay, so this part here, we have the amplitude of 1, so multiply by 3/2, so multiply by 1.5, it should have 1.5 as the highest amplitude, this part. Okay, for this part here, this one is 0.5 multiplied by this one is 0.5, right? Multiplied by 1.5, it should be something like multiplied by something like this approximately. Okay, as long don't have to draw with the really accurate scale, but as long as the highest one, you know that this is 3. Okay, the highest amplitude here, okay, reflects the gain given here. All right, okay, and I think that's it. Okay, so this is the answer for y2 omega. So basically we have answered question this final year as a question from question number 1. One last question. This is from past year test 2. So we have question 1b. Okay, this is from question 1b. Given a signal st as in a figure here, Sketch the signal yt if x omega has been transformed to the following transformation: y omega equal to this given equation. Okay, so again here we are given xt. Okay, we don't have x omega. Okay, but what we have here is x omega which has been transformed. Okay, and it is given by y omega. So if we look here, okay, we know that this is actually x omega which has been transformed using the Fourier transform properties backward. Okay, all right. So if we look at this equation, okay, we also observe from the properties of Fourier transform. Okay, so don't panic. Look at the properties of the Fourier transform and find the one that closely matches this equation. Okay, at the Fourier transform part. So from the table, okay, what we can see from the table of Fourier transform properties, we can find out that this is from the time transformation. F(at) minus t naught. Okay, if we perform the Fourier transform, we will get 1 over a f omega divided by a exponent negative j omega t naught over a. Okay, so we mesh with this equation. So f in this equation here is actually x. Okay, x omega. So we mesh with the equation. We look here. Okay, a here should be 2. Okay, f omega is x omega. If you look here, a is 2. Negative j omega t naught over a. Negative j omega negative j 4 omega over 2. So t naught here should be 4 because a here. Okay, so from here we know that f(at) minus t naught here is yt. This is basically yt is basically a signal that has been time transformed from xt. Okay, from xt. So yt here is x 2t minus 4. So again, why? Because yt is the signal that has been time transformed from xt here. So f here is x because f omega here is x omega. Okay, y omega here is the Fourier transform of yt. Okay, so we just put the equation here. A from the parameters that we have found out just now, a is 2, t naught is 4. Okay, so we get this. So the question here asks you to sketch the signal yt. Okay, basically you just need to use the knowledge that you have obtained from the first chapter, which is the time transformation. So we have xt. Okay, we have xt here. Okay, so what we can do here is we put this as tau. Okay, so we have tau. Okay, and the time involved is negative 4, 0, and also 4. Okay, so now what we can do is we put tau equal to 2t minus 4. Okay, and then 2t is equal to tau plus 4, and t is equal to tau over 2. Okay, and then we put tau in terms of this number, the time that involve any changes in the signal. So negative 4, 0, and 4. So when tau is equal to negative 4, 2, negative 4 divided by 2 plus 2. So negative 2 plus 2 is 0. Tau equal to 0. T equal to 2. Tau equal to 4. T will equal to 4 divided by 2. 2 plus 2. Alright, so for the new time involved here, okay, the matching time involved here, t, when tau is -4, t is equal to 0. When tau is equal to 0, t is equal to 2. When tau is equal to 4, t is equal to 4 as well. Okay, so okay, we will draw the whole signal based on this. Okay, if you notice that this only involve the shifting, okay, and also the scaling, doesn't involve any time. So we have time 0, 2, and also 4. Okay, so because it doesn't involve any inversion and also amplitude scaling, the shape should be the same. Okay, and this one should be so now we have answered the question for past year test 2, question B. Okay, so if you notice here, the question here needs your knowledge in chapter 1, okay, to draw the signal from the time transformation. Okay, so that's it for this video. Thank you very much.